Okay, so if some technical difficulty is there, hello, you are able to hear me, right?
Yes, sir.
Yes, sir.
Okay,
Yes,
if some
sir.
technical difficulty is there, that means my voice is, I mean, not audible, or suddenly some technical issue happens. You please type in the chat. Okay, so some audio is not visible. Okay, if it is only one person, I mean, getting that kind of problem, so it is problem from his end. If lot of people are getting, then I think it should be something from my end. Okay, so because I will try to switch off your mics for next 40 minutes, and in between if something is there I will ask technically, I mean technical issue is there or not. If something is there, you please type in the chat, okay, my audio is not visible or video is not visible or something like that, if something happens. Okay, right. So after that 40 minutes, after 40 minutes of discussion, then we will start discussing regarding your doubts if you have anything. Okay,
Is not
right.
available. Sir,
Is it clear?
Chat section is not available.
What?
chat option is not available. Like
Yes,
it's locked.
Okay, you it's locked.
It is available in mine.
Yeah, I think it is available. It should be available for everyone. Okay, I mean if you are in a mobile, yeah, if you are in a PC, it will be available. Okay. Anyway, if person who is available, if they inform me that something is there with my voice or video, it's stuck, then I think I will get the information. Then I will stop and try to rectify it. Okay, clear. Okay, then we will go ahead with our discussion. Right. So coming to DC circuits, I have already told it is divided into two parts. Just since it is little bit, it's better to break into two parts. That's the reason I have broken it. Okay. So sharing, I have not shared it, right? My video shared, right?
Yes, sir.
Yes, sir.
Yeah. Okay. Fine.
Yes, sir.
Okay. So DC circuits. I mean, the basic topics which we are going to cover in this part one is introduction part. And next, in introduction, we'll see what is voltage, current, some basic concepts related to power. Okay. And what are the different types of sources that are usually available in a DC circuit. Right. And we'll go through Ohm's law. Most of you may be knowing these things in your previous plus two or whatever it may be. But I will go through them briefly so that you'll have a recap of all these things. And we'll cover voltage and current laws, and when resistors are connected in series and in parallel, how your equivalent resistance is going to be. Okay, and voltage and current division rules will be there. Okay, so those things also we will discuss, and nodal and mesh analysis. So these all topics will be covered in DC circuit part 1. Right. Okay, so in introduction, starting from charge. So you know that there are basically two charges are present. One is positive charge, and other one is negative charge. Okay, so positive charge corresponds to protons. So protons are actually present within your element or an atom. Okay, so and these carry positive charge, and negative charge is basically corresponds to electrons. So electrons usually carry negative charge. Okay, so if you consider an electrical circuit, we are trying to transfer charge from one part of the circuit to other part of the circuit. Okay, when we are doing this, we are actually not going to change the total amount of charge, right? That means if you have a source, some energy is flowing from source to the load. Okay, but you are not actually creating any charge from somewhere, or you are not destroying the charge which is existing. If charge is generated, that means we are not changing the total amount of charge. It's going to remain same. That means it is flowing from one part to another part. Okay, and we are neither creating nor destroying electrons or protons when you are making your circuit to run, right? So the total number of electrons or the total number of protons which are present in your circuit remains the same when you are running your circuit. Okay, so we are not neither create nor destroy these electrons or protons present within your circuit. Okay, so coming to the unit of charge, you might be already knowing this. So unit of charge is denoted by capital letter C, which is called as coulomb. Okay, so unit for charge is coulomb. Okay, so similarly, if you have height, let's say some unit needs to be there to measure the height, so you will have centimeters or meters or kilometers or whatever it may be, right? So something like length you want to measure, you use that unit. Similarly, if you want to measure charge, it is like it is represented in terms of coulomb. So coulomb is the unit to measure charge. So what is I mean basic explanation for coulomb? It is defined in terms of ampere by counting the total charge that passes through an arbitrary cross section of a wire during an interval of 1 second. That means if you consider one particular wire, okay, there are a number of charge carriers, that means electrons maybe. Okay, so if you are standing at one particular cross section of the wire and trying to observe how much amount of charge is moving from left to right, let's say, okay, net charge which is flowing from left to right. So you'll keep on counting the total amount of charge in a duration of 1 second. Okay, you should, because if you give infinite time, infinite amount of charge will keep on flowing if some force is there for charge to move. Okay, but you should have a restriction, right? So in a duration of 1 second, how much amount of charge is moving, that is basically called as current. That unit is ampere. Okay, so this we are defining this coulomb, which is the unit of charge, in terms of amperes by counting the total charge that passes through an arbitrary cross section. That means if it's a wire, at any cross section you can consider, or the length of the wire. So how much charge is moving from one side to the other side if you are considering one particular cross section in that particular wire. Okay, so in a duration of 1 second, how much it is flowing. Okay, so it is basically both are interlinked. I mean, it is defined in terms of ampere. So you will see what is ampere or what is current. Then you will understand both are actually interlinked if you are talking about charge movement in a wire. Okay, so one direction you are considering. Okay, so this direction you are considering, and this is the cross section you are considering. So these are the individual charge carriers. So in a duration of 1 second, how much charge is flowing in one particular direction? Based on that, the net charge which has flown in 1 second, we are calculating that the unit is coulomb. Okay, right. So coming to, we have already discussed what is electron and proton. Okay, so single electron carries a charge of, it's a negative charge it will carry. So it is value is minus 1.602 into 10 to the power of minus 19 coulombs. Okay, one electron can carry this much amount of charge. If you consider a proton, it is the same value with positive sign. It contains positive charge, which is 1.602 into 10 to the power of minus 19 coulombs. This is the amount of charge which an individual electron or a proton consist of carries. Okay, so the quantity of charge that does not vary with time is represented by Q. So what does this mean? So you should have a notation for representing the charge. So Q is the letter which is used to represent the charge, and C is the letter, capital C is the letter which is used to represent the coulomb unit, right? So why it is capital Q, right? And because if it's time varying, that means if you consider a DC circuit, okay, usually it is not going to vary with respect to time. So we usually represent all DC related things with a capital letter. Okay, it's not wrong that even if you represent with a small letter, okay, small q if you represent, it is not wrong. As far as DC circuits are concerned, you can represent either with a capital letter or small letter also. There is nothing wrong. If you represent with small letter, then you have to specifically say it's a DC circuit, so Q remains constant, right? But if it is varying with respect to time, okay, the instantaneous amount of charge which may vary with respect to time is usually represented by small letter q. That means if it is varying with respect to time, you have to represent with small q. Okay. If it is not varying with respect to time, you can represent with small q or capital Q. That is your choice. Clear? Okay. So varying with respect to time, usually use small letters. In any case, it may be a charge or voltage or current. If it is varying with respect to time, you have to represent with a smaller alphabet, right? And if it is not varying, it's your choice. You represent with small letter or capital letter. It's up to you, right? There is nothing wrong. Okay. So Q is the one which is used to represent the charge, and C is the one which is the unit for the charge, which means coulombs. Okay. So charge is there in a obviously if you consider any conductor material, let's say wire, electrons are present within that. So these carry some amount of charge which is already present with them. Okay. Right. So when you talk about current, charge staying at one point does not represent any current. Okay. Right. Charge in motion represents a current. If you are trying to move the charge, then obviously some amount of current is going to come into picture. Okay. So charge in motion only will represent current. Right. Okay. So coming to current, if you consider a metallic wire, that means a conductor. Okay. If you want to represent a current, it will have two parameters. You can that is, one is a numerical value. That means the magnitude, how much the current is flowing. That should be represented by you, and the direction associated with it. Okay. And in what direction your current is flowing or your charge is moving. Okay. So if you want to represent current, you have to have the magnitude and direction both represented. Then only the representation of current makes some sense. Okay. If I say 3 amperes and if I don't represent direction, that is basically doesn't make any sense, because it leads to confusion in which direction your current is flowing. Okay. So whenever in any circuit, if you are representing current, these two are compulsory, right? One is magnitude, that is numerical value, and the one is direction in which it is flowing, right? So so for current you have to remember these two. So what is basically current is nothing but charge in motion represents current. So how to define this current? It is a measure of the rate at which charge is moving past a reference point in a specified direction. Both are linked actually, because charge in motion represents current. So obviously the current is nothing but something which is linked to charge. So how it is defined? The rate at which the charge is moving past a reference point in a specified direction. So that means in one particular direction, how much amount of charge is moving with respect to time. That means you consider 1 second, right? So in 1 second, how much charge is moving from left to right, net charge flow. That represents your current. Okay, so that is given by this expression, I is equals to dq by dt. Okay, so if you consider dt is equals to 1 second, and how much charge is flowing in that 1 second in one specific direction, that will give you your current flowing in that particular wire, right? So next is current in an electric circuit is due to negative charge motion. So you know the protons are present within the nucleus, and the electrons are present in the outermost orbit. So it's basically the electrons, which are the negative charge carriers. They are trying to move from one part of the circuit to another part of the circuit, or they are actually transferring charge from one electron to another electron. You understand, right? So charge motion is actually happening because of electrons, right? So electrons will transfer charge from one part to another part. So basically it's the negative charge which is actually moving in an electrical circuit, right? Is it clear? So I is equals to dq by dt. So what is here? Also same thing, the unit for current is amperes. You already know the unit for current is amperes. If you see this equation, I is equals to dq by dt, so amperes is also called as coulombs per second, right? Because dt represents, let's say, in seconds, and dq represents some amount of charge which has moved, so it is coulombs per second. So ampere or coulombs per second, both mean the same, right? So in shorter form, we are calling it as ampere. So how to denote this current? Similar to previous case, if it is instantaneous current, that means it can be varying with respect to time. You represent with small letter of I, and if it is a constant value which is not varying with respect to time, you represent with a capital letter I. Okay, so this is a brief explanation regarding your current, which is basically charge in motion given by I is equals to dq by dt. You should remember the direction is very much important, and the numerical value is also very much important. Clear? So here I am giving a brief, pictures of different types of currents which can exist. Okay, so if you see the figure A, the current magnitude is going to remain constant with respect to time. So obviously we'll call it as DC current, which is direct current. Okay. In figure B, you could see something which is varying with respect to time. That means the magnitude of your current is actually varying with respect to time. So it is varying in a sinusoidal fashion. So we'll call it as sinusoidally varying current. Okay. So in figure A, you can call it as, you can represent with capital letter of I or small letter I. There is no issue. But in B, you should compulsorily represent with small letter. Right? And figure C, if you see, it is something which is varying with respect to time, and it is exponentially varying. So the current is varying exponentially. One is varying sinusoidally, one is remaining constant, and the one is exponentially varying. Correct. So this is a brief explanation I want to show regarding different natures of current. In this circuit, we will mostly deal with DC current, that is constant value. When we go to AC circuits, then we will deal with alternating currents. Okay, so graphical symbol for carrying current is placed next to an arrow. So I have already told, right, to represent current in a wire, we should have two things. One is numerical value, which is magnitude, and the one is direction. So if you see here, I have shown 3 amperes of current. That means 3 coulombs per second is actually flowing from left to right. That means in the direction of arrow mark. Okay. Right. So this is the way you actually represent the current which is flowing in a wire. Okay. Right. So the same thing, if you see the below point, above figure indicates either a net charge of 3 coulombs per second is moving to right, or that a net negative charge of minus 3 coulombs per second is moving to the left each second. What does this mean? It means when 3 amperes of current is flowing, it means that 3 coulombs of charge, positive charge, is moving from right to left. I can visualize this in another direction, right? How it is? Minus 3 coulombs of charge is actually flowing from right to left. Clear? So that means same figure, if I change the arrow direction and place minus sign in before 3 amperes, that is also true. Both are correct. Right? So positive charge is moving from right to left, or minus 3 coulombs of charge is moving from left to right. Both are right. Okay. There is nothing wrong. You speak in both direction. So why I'm speaking regarding this is, you should understand in general system, in electrical real system, or in standard system, standard books, the current direction is usually considered as the direction of movement of positive charge. It is clear that we know that it's the electrons which are moving. That means it is the negative charge which is moving. Correct. It is the negative charge which is actually moving, but the convention we usually follow is the direction in which your positive charge is moving. Okay. So current is always represented in the direction in which your positive charge is actually moving. Okay. Even though it's the negative electrons which are carrying your charge, I am taking the standard convention is the direction in which your positive charge is moving, that is considered as your convention for you to represent your current. Okay. In the below example, you will understand. Okay. So it is convenient to think of current as a motion of positive charge. Okay. Right. So previously I told positive charge is moving from right to left. So that means your current direction is from right to left. Okay. Right. So that means what it means is your electrons are actually, okay. So in this figure, 3 amperes of positive charge is actually flowing from left to right. Right. So that means minus 3 amperes of current is actually flowing from right to left. So that means minus 3 coulombs of charge per second is moving from right to left. That means electrons are flowing in this direction from right to left, which are carrying negative charge. So that it indirectly means holes are moving from left to right. So that means the direction in which your holes are moving, or the direction in which positive charge is moving, that is the direction in which the current is actually flowing. I hope I am clear, right? So always, if electrons are flowing in one direction, your current is actually flowing in other direction. That is the standard we follow. Clear? So the direction of electrons and the direction in which your current you are representing are both opposite. That is the standard convention. Current direction is the flow of holes. Right. Current direction is the flow of holes, not the flow of electrons. Current direction is opposite to flow of electrons. Current direction is in align with the flow of holes. Okay. So that is positive charge movement. Right. So for you, for example, if you see here in the figure below, electrons are moving from left to right to create a current of 1 milliampere, right? So electrons are actually moving from left to right, from here to here. So that means electrons carry which charge? Negative charge. So they are moving from left to right to create a current of 1 milliampere. Okay. So they are flowing in this direction. So determine I1 and I2. I am clearly saying that electrons are moving from left to right. The electrons are moving in this direction. That means negative charge is moving from left to right. So the magnitude of this current should be something which is negative value. Correct. So I1 is represented as minus 1 milliampere. Because electrons carry negative charge and electrons are moving from left to right, I told. So from left to right, electrons are flowing, electrons carry negative charge. So your magnitude of current I1 is minus 1 milliampere. Clear? Because I told it's already, they are trying to create a current of 1 milliampere. So I1 is minus 1 milliampere. So if you see that in the opposite direction, electrons are moving in this direction means negative charge is moving in from left to right. So positive charge is actually moving from right to left. That means from here to here. So the current I2 should have a positive magnitude. So that means I2 will have 1 milliampere. Okay. You blindly remember, if electrons are moving from left to right, your current direction should be represented with in the opposite direction. If the electrons are moving from left to right, your current direction is positive value is from right to left. That's what is happening here. Electrons are moving from right to left, and your current value will be positive if you are moving from here to here. Is it clear? So it's as simple as it is opposite to the direction of electron movement. Electrons carry negative charge. Okay, so opposite to electrons movement means positive charge is moving opposite to electrons. So positive charge is here I2. That means I2 will have a positive value and I1 will have a negative value. Clear? So this is the convention. This is the standard convention in all the textbooks. Even in the real system, people will follow this thing. If someone is saying that some from next room to this room, current of this much is flowing, it means it is the flow of positive charge which is flowing from next room to this room. Okay, it's not. It is actually opposite to flow of electrons. Clear? I hope I am clear. Anyway, if you have doubt, we'll discuss this in the last part. Okay. So coming to voltage. Okay. So we have discussed regarding charge. We have discussed regarding our current units. We have discussed. Okay. So how this charge can move in a wire, in an electrical wire, if you see. Okay. It can't move on its own. Some force is required. Okay. Something needs to be forced, then only it will move in an electrical wire. So what is that force? We should define it, and we should know what is that force. Okay, so considering a general element shown below, let's say this is your element. Any element, I am simply saying, we don't know what is that element. Some element is there. Okay, so pushing of charge or current through the element requires an expenditure of energy or work. That means if I want to push some amount of charge from terminal A to through this element and back to terminal B, some amount of work or some amount of force or some amount of energy needs to be spent, right? Otherwise, without any force here, your electrons will remain stationary in the entire part. Nothing is going to flow into your element. Electrons will remain here only, that's all. When I create a force, okay, any physical force means if you push with hand, it will go. For an electrical circuit, it is a voltage, which is the force, which is creating the force for the charge to move or current to pass from terminal A through the element to terminal B. So that means we can define voltage. That means the pushing of charge or current through the element requires some expenditure of energy or work. We can say electrical voltage or potential difference exists between terminals A and B. That means if some force is happening and some current is flowing from terminal A to element and from element to terminal B, so it automatically means some amount of force is present at terminals A and B, which is called as voltage. Okay, so without any voltage or a force available between terminals A and B, no current or no charge will flow into this element. Okay, so that force is basically created by voltage. Okay, you understand? So considering an electrical general element, pushing of charge or current through the element requires some amount of energy. Okay, that energy is nothing but which was created by voltage. Okay, so we can say electrical voltage or potential difference exists between terminals A and B. Okay, so something is flowing means obviously some voltage is existing between terminals A and B. So what is the definition? The voltage across the terminal pair is a measure of the work required to move charge through the element. Okay. So I am saying some amount of charge is flowing. So we are defining this voltage in terms of the amount of work required to move charge through the element. Okay. Let's say some amount of work is spent in moving 10 coulombs of charge. Okay. Okay. So that work done divided by that 10 coulombs gives you voltage. Is it clear? So electrons are present without any force existing. There is no motion. There is no movement of electrons or no movement of charge. So there is no current. Okay. When you create a force, obviously, which is when you connect to a voltage source, obviously that voltage source will spend some amount of energy or some amount of work will be done by that fellow. Then only charge will move. That means electron movement requires some amount of work to be done by some force. That force is created by voltage. Okay, so voltage is actually represented by, similar to previous case, capital V or small v. Okay, if it's varying, you should compulsorily represent with small v. If it is not varying, you can represent with capital V. No issue. Okay, what is the unit for voltage? It's volts. Okay, unit for voltage is volts. Right. So 1 volt is same as 1 joule per second. In the previous case for current, you have seen ampere is equals to 1 some coulombs per second. Okay, voltage is basically joules per coulomb. That means how much amount of energy or how much amount of work in joules you are utilizing or you are using to transfer coulombs of charge from terminal A to terminal B. Okay, so this unit is work done per coulomb. Okay, clear. Let's say work done 5 joules per coulomb. That means 5 joules of energy is spent in moving a charge of 1 coulomb from terminal A to terminal B. Okay, let's say 100 joules of energy is spent in forcing 10 coulombs of charge from terminal A to B. So the 100 divided by 10, that means 10 joules per coulomb, that is 10 volts. Okay, right. So it's basically work done per coulomb. That is the unit for joules per coulomb is a unit for voltage, which is also represented with capital V, which is volt. Okay, so next question is, if you see here, voltage can exist between a pair of electrical terminals where current is flowing or not. You understand, I hope so. Voltage can exist between a pair of electrical terminals whether a current is flowing or not. In the previous class, I have told if you straight away touch the 230 volts supply, and if you are standing with a good footwear, right? Good footwear means with wearing rubber and good insulating material. Current will flow to your body, but at your footstep it will stop, right? That means it doesn't mean that voltage is not existing. Voltage is existing, coming from the plug point into your body, and it is stopping at your footwear, right? So that means voltage can exist between a pair of electrical terminals whether the current is flowing or not. So even current is not flowing, if you measure the voltage at your foot step, okay, at your fingertip, leg fingertip, you will find some amount of voltage is present. Okay, so what it means is even though current is not flowing, voltage can exist between a pair of terminals. Is it clear? So in that example, if you connect a voltmeter between your fingertip of your leg and earth, you will observe some amount of voltage existing across that insulating material. That means your footwear, whatever you are wearing, made up of rubber, right? That means voltage is existing, but no current is flowing through your insulating material, right? So that means if current is zero, it doesn't mean that voltage is zero. Voltage can have a finite value even though current flowing is zero. Okay, so we have seen current is actually represented with an amplitude. With an amplitude means with a numerical value and a direction. Now if you see the voltage, how to represent a voltage? Voltage should be indicated with a plus minus pair of algebraic signs. That means if I say 5 volts, okay, so let's say here it is 5 volts between A and terminal, let's say 5 volts. If I don't give plus sign, minus sign here, or minus sign, plus sign here, it doesn't make any sense. Okay, you are saying that the voltage difference between terminal A and B is 5 volts, but you are not specifically saying which terminal is at a higher potential or which terminal is at a lower potential. In this, if you see, let's say between terminal A and B, if I say 5 volts, it means that voltage of 5 volts difference exists between terminal A and terminal B. Okay, 5 volts is the voltage difference between terminal A and terminal B. That's what it means. But you are not specifically specifying whether A is at a higher potential compared to B or B is at a higher potential compared to A. Okay, you are saying only the potential difference is 5 volts, right? So to make sure that to represent that, you have to give plus sign and minus sign pair for of algebraic signs to any voltage if you are representing. Anyway, once you go to next slide, you will understand. Okay, so explanation for voltage polarity. So if you see here, I mean, to make you a clear picture, I have represented all these 4 figures. If you consider this, let's say, some element, and the potential difference between these two, they are saying it as minus 5 volts. So you should always first represent plus sign and minus sign. It can be opposite also. This can be minus and this can be plus. No issue. Okay. So what this kind of representation mean? So if you see in figure A, the difference between those two is 5 volts difference. But which one is at a higher potential and which one is at a lower potential, that you have to understand. Okay. If this minus sign is not minus and if it is plus, you can straight away say that plus terminal is 5 volts ahead of this negative terminal. That means A is positive higher than B by 5 volts if it is plus sign. But if you see in this figure, I have intentionally made it minus sign. So what does this mean? It means that A is minus 5 volts ahead of B. Or we can say in the alternative way, B is 5 volts positive with respect to A. Clear? B is 5 volts positive with respect to A. Understand? If you see here in figure B, it's straight away a positive sign. So it directly means that this is plus sign, this is minus sign. That means B is 5 volts higher than A voltage potential. Clear? If A is 0 volts, B is 5 volts. If in case A is 5 volts, B is 10 volts. Understand? We are actually representing only the potential difference between these two terminals and it is positive sign. So it means that B is 5 volts higher than A value. If A is 0, this is going to be 5. If A is 5, this is going to be 10. If A is 10, B is going to be 15 volts. Okay. This is how you have to represent. This is very important for you to understand. Okay, because all electrical circuits, whatever we discuss in the entire course, this polarity representing of voltage and representing of current is very important. You should have a clear picture of these things, then only you will be able to understand the next topics without any confusion. So coming to this one, this is pretty simple. Straight away you will be understanding. It means that this is positive and this is negative. That means this is at a higher potential compared to this fellow, and this is 5 volts. So what it means is A is 5 volts higher than B. That's what it means. Clear? Here B is 5 volts higher than A. Clear? Here also if you closely observe, okay, A is minus 5 volts with respect to B, or we can call it as B is plus 5 volts with respect to A. Okay, so that means these two are almost same. These two are identical. These two are similar. Okay, so in these two cases, B is 5 volts positive with respect to A. If you consider these two, A is 5 volts positive with respect to B. If you observe this also, they are saying that B is minus 5 volts ahead with respect to A, or it directly means A is plus 5 volts ahead with respect to B. That means these two are same. So in figures A and B, terminal B is positive with respect to 5 volts positive with respect to terminal A, and in terminal C and D, it is A is 5 volts positive with respect to terminal B. Okay. I hope you are able to understand. If you have confusion, think about this, take some time and think about it, then you will come to a clear picture. Okay. If you have a lot of confusion when you are dealing with circuits, simply what you do is this minus sign, you make it plus and you interchange these two polarities. Okay, that will avoid your confusion when you are dealing with circuits. Okay, there is nothing wrong, both are same. That means you are converting this into this format. Clear? So you make this one positive, this one negative, and make this minus plus sign. So there is nothing but this one. So these two are both are same. They will not create any difference when you are solving your circuits. Okay, if you feel confusion with this negative polarity, simply convert into this fashion and solve your problem. No issue. Right. Similarly, these two are identical. If you have minus sign, convert this into this format. Simply change the sign and change the polarities of these two. Make plus into minus, minus into plus. That's all. Clear. So for you to understand, here I have given one example. So the magnitude of V1 is given as 17 volts. Okay. And polarity, obviously I can't represent in text. It should be with respect to your figure. Okay. So they are saying that V1 is 17 volts. So V1 is, this is positive, this is negative, and 17 volts exist between these two terminals. And what it means, this positive terminal is 17 volts ahead or 17 volts higher compared to this terminal. That's what it means. So then what will be V2? Obviously I told, right? If you are changing the polarity, then you change the magnitude. So here if you see in terms of V2, the polarity they have changed. This plus has become minus and this minus has become plus. So if you want these to be identical, since they have given this as 17 volts, this should be equals to minus 17 volts. So that means in this circuit, V2 is equals to minus 17 volts is same as V1 is equals to 17 volts. Both are same. Clear? So if you represent only this thing with this, it's correct. If you only represent this thing with this minus sign, that is also correct. Both are same. Clear? So voltage always exists with a plus and minus sign representation and some numerical value. Clear? Current always exists with a direction and a numerical value. That means magnitude. Clear? So make sure that this you are very pretty clear with this voltage representation and current representation, because when I ask you to calculate power, it's a combination of these two which you have to calculate. So that's why make sure that you don't have any confusion with respect to these representations. Okay. So coming to power. Okay. So we have seen what is current. We have seen what is voltage. Okay. Current is flow of charge. For flow of charge to exist in a wire or flow of charge to be taking place in an element, some force is required. That force is actually created by the voltage. That means voltage is something, the amount of force which you are creating to move charge from one terminal to another terminal. Okay. So power is basically a combination of these two. So how it is defined is voltage has been defined in terms of energy expenditure. That means the amount of work done. Correct. And power is defined as the rate at which that energy is expanded. Right. So for creating charge movement, voltage that means some work is done. That work is represented in terms of voltage. And when it comes to power, how much amount of energy you have spent with respect to time. That means the rate at which that energy is expended, energy is spent. So that is basically called as power. So we represent power with a capital letter P or a small letter p. Okay. If it's varying with respect to time, obviously small letter. If it's constant, then you can use capital letter. What is the unit for power? It is watts. Okay. So current ampere, voltage volts, power is watts. Okay. So power absorbed must be, it's a combination of basically if you see the energy spent, okay, in moving charge with respect to time. So it's basically a combination of both voltage and current. So power absorbed must be proportional both to number of coulombs transferred per second, right? You are transferring some amount of charge in a duration of 1 second. So that is basically current. It is proportional to current. And to make this current to flow, you require some energy. Okay. So and to the energy needed to transfer 1 coulomb through the element, right? Okay. So current flow is there. Current flow cannot happen on its own. Some amount of energy needs to be spent. That amount of energy spent is basically in moving 1 coulomb of charge is basically voltage. So power is proportional both to voltage as well as current. Clear? So power is equals to V into I. Unit is joules per second or watts. How this joules per second has come? If you see current, let's say if you see voltage is joules per coulomb and current is coulombs per second. So if you cancel coulombs in the numerator and denominator, it will be joules per second which is left. Right. So what is basically power is? It is the amount of energy which is expended in moving a charge of 1 coulomb in a duration of 1 second. It means that, right? The amount of charge you are transferring in a duration of 1 second and how much energy you have spent in moving that charge. Okay, so it's basically proportional to both V and I. Okay, so we can say that, okay. Clear. So we have discussed regarding voltage, current, and power. Now the question comes whether the element is absorbing power or delivering power. Okay. So the question is whether the element is absorbing power or delivering power. How to know this? Okay. So to know this, we should have both voltage and current. Then only I can say whether this element is absorbing or delivering power. Okay. So for me, if you ask me how much amount of energy power is being absorbed by this element, I should know voltage across this element as well as current which is flowing into that element. If I know these two things only, then only I will have the ability to say whether the power is absorbed by the element or delivered by the element. Okay. Then only I can clearly say. Otherwise, I will not be able to say. Okay. So any element, if you want to know what is the amount of power being absorbed, first of all, you should know these two. Voltage across these two terminals and current flowing into that element. Then only you can say, if I ask power absorbed, you can say some value. If I ask power delivered, you can say some value. So without giving these two parameters, if I simply ask that how much power is absorbed, that is senseless. Okay. My question itself is wrong. Okay. So you should know these two, and then only you can say power is absorbed or delivered. So if you see in this figure, we can say power absorbed by the element is V into I. Okay. So why this P power is positive in this case? Okay. This is very important. You have to understand when I say power absorbed, always think only one thing. Current flowing into positive terminal you consider. Current flowing into positive terminal I have to know. Okay. So here it is V. That V is plus or minus, don't mind. Okay. Current flowing into this positive terminal I have to know. This current can be positive or negative. I won't mind. Okay. If I know the current flowing into this positive terminal has some value, it can be positive or negative, I won't mind. If this value is V is given, it can be positive or negative. So power absorbed is simply the current flowing into this positive terminal into the voltage across these two terminals. Okay. Power absorbed is always represented in this fashion. It is a standard notation. Okay. Power absorbed is always the product of voltage and the current which is flowing into the positive terminal of that particular voltage. Clear? So always try to consider only the current flowing into this positive terminal and simply multiply that current with this voltage. That is called as power absorbed. That means power being drawn by the element or power being consumed by the element. Okay. There is a major difference between power absorbed and power delivered. Okay. That anyway will come to know. Okay. So when we say about power absorbed, whether it can be an element or it can be some source, whatever it may be. Right. Always. Anyway, this you have to represent. Without this, you will not. It doesn't make any sense. Question doesn't make any sense. Voltage should be represented. Current should be represented. Okay. Okay. So simply multiply the current flowing into the positive terminal of that particular voltage with the voltage value. That's all. That will give your power absorbed by that particular element. Right. So to make you pretty clear and without any confusion, I have given you 4 figures here. Okay. Current flowing is always from into that. If you consider this is your element and I am asking, so let's consider the C case first. It will avoid your confusion. Okay. So if you see here, this is your element and this is positive terminal and this is negative terminal. That means A is 5 volts ahead of B. Okay. So A is at a higher potential and B is at a lower potential. The difference between those two is 5 volts. Current flowing into the positive terminal is 2 amperes. So what is the power absorbed by this fellow? Simply current flowing into the positive terminal into the corresponding voltage. 2 into 5. That is 10 watts. Clear? let's see this case, D case. Okay. Actually, both are same. If you see here it is plus sign, here it is minus sign. So that means you can interchange this plus to here, and you can say this minus here, and you can consider this as positive value. I hope you are able to understand. Okay. Right. So this is also plus 10 watts. Power absorbed by this fellow is equals to 10 watts. Okay. If you don't want to change this, you go deep into this. So 2 amperes is flowing in this. So obviously 2 amperes should come out in this direction. Right. So 2 amperes is coming out. So what is the current which is flowing your positive terminal? Minus 2 amperes. Since this is 2 amperes here, it will keep on coming in this fashion. So plus 2 amperes is coming out. So which means minus 2 amperes is flowing in. So minus 2 amperes into minus 5. I told you, right? Current flowing into the positive terminal, you simply multiply with the voltage shown here. That's all. So current flowing into the positive terminal will be, if this is 2, this will be 2 coming out. So that means minus 2 is 1 which is flowing in. So current flowing into the positive terminal is minus 2 amperes. So minus 2 multiplied with minus 5, that will give you plus 10, that is again 10 watts. That means these two circuits are same. These two circuits are similar or identical. Okay. If you see here, right, current flowing 2 amperes is coming into this terminal. That means current is coming in this fashion and it is flowing out in this fashion. So that means 2 amperes is flowing out of terminal B, because terminal B is positive here, right? That means 2 is coming out. So minus 2 is flowing in. So minus 2 into plus 5 is minus 10 watts. So power absorbed by this fellow, this element, is minus 10 watts. Clear? If you change the sign for this one and alter these two terminals, these two are same. So here also minus 10 watts is absorbed by this element. Remember, this is absorbed power. Power absorbed is always the current flowing into the positive terminal of your voltage. The voltage magnitude may be minus 5 or plus 5, you don't mind. You simply try to find out what is the current flowing into the positive terminal of that particular voltage. Simply multiply that current with the voltage. Voltage can be plus 5 or minus 5, whatever it may be. If you observe here, that's what is going to happen. Current flowing into this positive terminal is 2 amperes and the voltage I have given is minus 5. So 2 into minus 5 is minus 10. That's all. If you want to change this, make it plus 5 and alter these two terminals. So there is minus sign and plus sign. Again, if you calculate, it will be the same. That means minus 10 watts is the power absorbed by these two elements. Absorbed means that much amount of power is actually flowing in to that element. Absorbed means power which is drawn by the element, power which is consumed by the element. Okay, so consumed by the element or absorbed is minus 10 watts in these two figures and plus 10 watts in these two figures. Clear? I hope you understand. So right. So I think I should stop here. Maybe we'll discuss these things in the next class. Okay. Hello.
Yes, sir.
Yes, sir.
So you all are here, right?
Yes, sir.
So
Yes,
so did you understand? I mean, the basic representation of voltage, current, and power.
Yes, sir. Got it.
Yes, sir. Got it, sir.
So please go through this terminology and this representation. This is very important because next question something. If you see here, I will ask what is the power consumed by this element or power delivered by this element. Okay, so that time you should be able to answer. Okay, so go through this because this is pretty important when you go for next classes. Okay. Right. So if you have any doubts, make a note of it. And next time when I come to class, you simply ask me. I will try to answer those. Okay.
Okay, sir.
And I think, yeah. If you have doubt, if you have any doubt now,
Share the slides. No, sir.
yeah.
Please share the
What?
slides.
See. This video, whatever I have explained till now, that is already recorded. Okay. So these recorded things I will send you. But I should get an official mail ID from the office. So we have already requested. So if possible today I will send, or otherwise after tomorrow's class I will send you. Okay, because I can send only to official mail ID. It will not allow to individual personal mail IDs. Okay. So we have requested office. They will give the So once they give their mail IDs, I will surely send the entire recorded video. You can go through it and understand again. Okay. Okay, then fine. I think time is up. Yeah.
Sir, in general, current flows from a higher potential to lower potential, no, sir.
Yeah, correct. So
Sir,
current actually,
how can it flow from a negative terminal to positive terminal, sir?
see, if I say it is flowing from negative terminal to positive terminal, obviously your current magnitude will be negative. See, if you see here in this figure slide you are able to see, right?
Yes, sir.
Yeah, so this is correct.
Sir,
This
in the
is
different slide you showed us the power, no, sir. There I got the doubt, sir.
where here,
Yeah, this one, sir. Yes, sir.
this one. So which one, which figure you exactly say?
Yes, sir. In that figure, you had put 2 amps, no, sir. It's flowing from a negative terminal to positive terminal.
Yeah. Okay.
Yes, sir. Please explain.
Okay. So current actually flows from positive terminal to negative terminal from the source. That is, you are talking in terms of source terminals. Okay. So this is not source actually. This is I am considering as an element which is consuming power. Okay. Right. Current actually what you have told is correct. It is positive source to negative source. Let's say I have two sources. One is 5 volts, another one is 2 volts, and both are connected opposite to each other with one resistor element. You understand the scenario? One is 2 volts, and the one is 5 volts. In between, I have one 10 ohms resistor. Okay. Then, if you see the current which is coming from 2 volts will be opposite to the current which is coming from 5 volts. Both are forces. Both are trying to force charge in either direction, in opposite direction. You understand, right?
Yes, sir.
Okay. So when that kind of situation occurs, you should speak about only one specific element. Okay. Okay. So if you say that current always flows from positive terminal to negative terminal, if I have a 2 volt source on left hand side and a 5 volt source on the right hand side, and in between I have some n value of resistance. Okay. So 2 volts will be trying to force current from left to right, and 5 volts will be trying to force current from right to left. Both are opposite to each other. Okay. Then it is the numerical value of individual current which is flowing from right to left. One magnitude is flowing, from left to right another magnitude is flowing. So you have to take the algebraic addition of both. Okay.
Okay, sir.
Okay. So if you see that in the other direction, even though it is positive terminal, your net current will be only in one direction. Okay. You understand? Okay. So anyway, so you can't blindly say it is from positive terminal to negative terminal. If I have a source which is higher potential and higher energy to force current in opposite direction, then it is opposite to that. Okay.
Okay, sir.
Don't get confused. Yeah. Don't get confused. You go through these slides, you will understand.
Sir, I have a doubt.
Okay.
Sir,
You have any class now or not?
Sir, 11:20.
Okay, fine. Okay. Let's say your doubt.
Sir, I have doubt that why neutral bodies are attracted by, light neutral bodies are attracted by charged bodies. We have already studied, and some basic concepts are there, like attracts, like charges repel, and unlike charges attract. But sir, here it is neutral. Not charged.
This is neutral. This is neutral.
This is still why it gets attracted by charged bodies. It is said that light neutral bodies are attracted by charged bodies, just like piece of papers.
See, it's basically if something is getting attracted, it's because of charge difference. Okay, voltage difference. So if you see here, okay,
Yes, sir.
or I am not actually exactly understanding your question, but basically what it indirectly means is current will try to take the path which has minimum resistance. That means if you have different paths, current will try to flow where the resistance is low. In that direction, it will try to flow. It's the same way with the charge. If you have a constant potential, okay,
Yes, sir.
right, and if you have two parallel paths, okay, so charge flow is nothing but current flow. Current flow is nothing but charge. Okay, so in which direction you have less amount of resistance, that direction current will flow. Okay, if you talk in terms of charge also, it is the potential difference which is creating that charge to flow.
Yes, sir. Sir, I can understand slightly. I will ask
Mm,
further, and then, sir, there is one more question.
Okay.
Sir, I am feeling potential should be dependent on resistance.
No. It's a misconception. Resistance is not a source. Resistance is only one which can consume power. Okay.
So like just if we think of a metallic conductor, if we are applying a potential difference, and the more resistance it will have, the more work we will have to do to move that charge in that conductor. So there should be a more potential difference between that, so that we can move charge on that conductor in that conductor.
Okay. So first you have to. I mean, this thing. How I can say is, what is. I mean, let's say you are going in the opposite direction. You are thinking in the opposite direction. It is the
Yes, sir.
voltage is the king. That means it's the voltage is the king. Because of voltage existing, only charge is going to exist, or current flow is going to exist. It's not that because of current existing, voltage is existing. You understand? So the king here is voltage. Voltage will determine. Okay.
Yes, sir.
Let's say voltage is 230 volts I have given. Okay, I can connect a small fan. I can connect a very big motor to it. Okay, but the voltage is fixed. Okay, so the force, which is 230 volts, the force or the energy that is available at 230 volts is always fixed. It is not going to vary. What kind of element you connect on the other end, it is immaterial. It is 230 fixed, right?
Yes, sir.
So if the resistance of the element is high, obviously
Yes, sir.
less amount of current will flow. You are understanding? Okay. So here the voltage is the king. Voltage is the king, and nothing is going to change me. I am going to remain fixed, stiff. Okay, that's called as battery. 230 volts from the source, or a battery voltage of 12 volts. It is going to remain same. Okay,
Yes, sir.
and whatever you are connecting to that will create some opposition force. Let's say resistance of 5 watts, resistance of 5 ohms or 10 ohms. So that is going to create some opposition. So current has to flow against that. Okay, you are understanding? Okay.
Yes, sir.
So current obviously will depend on the nature of the element what you are conducting. It indirectly means the nature of the resistance of the particular element. Element will have some resistance. That based on that resistance, this current magnitude will be depending on that. But voltage is going to be fixed.
Yes, sir.
Okay.
I mean, we can say that current compensates that effect.
Yeah, that means if you say indirectly, the amount of energy which was spent, okay, that should be deposited somewhere else, right?
Yes, sir.
So from voltage, some amount of energy is flowing. That means some amount of charge is flowing. Where it should go? It should be consumed at some other point. That consuming element is nothing but resistance. So that energy is actually consumed by the resistance, and it is converted into heat. So it is converted into heat energy. So the energy which was delivered from the source is consumed at the load. Right. So you can't create energy, you can't destroy energy. Energy can be transferred from one form to another form. So it's an electrical energy here which was converted into heat energy in the form at the output of the resistor. Clear.
Yes, sir. Okay.
Okay.
Thank you.
Okay. Okay then. Fine.
Thank you, sir.
Yeah, thank you.
Thank you, sir.
Yeah, thank you. Thank you. Please carry on for your next class. Yeah.